Hello students, let us start our today's session from organic chemistry, the chapter haloalkanes and haloarenes. How haloalkanes and haloarenes are formed? These are the derivatives of alkanes and arenes. Arenes are benzene compound and alkanes are the saturated one. So haloalkane and haloarene can be represented as Rx, ARX. How Rx and ARX are produced? See, the general formula for alkane is RH. So, in which one of the hydrogen is replaced by the halogen. So, the name is given alkyl halide or its IUPAC name is haloalkane. Similarly, we can represent benzene as ARH. So, in which the hydrogen is replaced by the halogen, so it gives aryl halide or we can say it as haloarenes. Here the X is either chloride or bromide or iodide. Why do we learn about haloalkanes? Haloalkanes and haloarenes, they play an important role in our daily life. For example, halothane. It is used as anesthetics. Halothane is trifluorobromochloroethane, that is called halothane, but it is used as anesthetics in medicine, as well as chloramphenicol chloroquine or antibiotics. Chloramphenicol, which is extracted from soil microbes and it is given treatment for bacterial infection. Similarly, chloroquine, it is an anti-malarial drug, so which is taken for the treatment of malaria fever. This is the reason why we need to learn haloalkanes and haloarenes. Not only this, it widely spread over our daily life as well as for industrial purposes. Classification of haloalkanes. This classification can be made depends on the hybridization involved in carbon atom and the number of halogens present in a given compound. See, if we have only one halogen in our compound, then it is said to be monohalo derivative, that can be given by the formula RCH2X or C6H5X, in which one more hydrogen, when it is replaced by another halogen, it is said to be dihalo derivative, or in the alkyl group all the three hydrogen atoms are replaced by the three halogen, it is said to be trihalo derivative. Similarly, in the benzene ring we can replace one or more hydrogen atom with respective halogen atom. So when one hydrogen is replaced, I will get halo benzene. Here I am getting 1,2 dihalobenzene and it goes 1, 2, 3 trihalobenzene. So based on number of halogen, we can classify the haloalkanes as well as arenes. And the next one, based on hybridization. Hybridization, we have the carbon with the sp3 and carbon with the sp2. If the halogen is attached with the sp3 carbon, then those are further classified into alkyl halides, allyl halides and benzyl halides. Or if the halogen is attached to sp2 carbon, then it is divided into vinylic halides and aryl halides. Aryl halides are the aromatic halo compound in which the halogen is attached to sp2 hybridized carbon. Vinyl is nothing but ethenyl group. Ethene, we have the formula CH2 double bond CH2, in which one of the hydrogen is replaced by halogen. So this ethenyl group CH2 double bond CH is said to be vinylic, in which the halogen is attached to the doubly bonded carbon system. So these two comes under the hybridization, where carbon it has sp2 hybridized carbon. Let us see now sp3 hybridized carbon. This is further divided into alkyl, allyl and benzyl. Allyl is nothing but a propenyl group. So allyl is a propenyl group. So in this propenyl, I have the CH3 carbon at sp3 hybridized and other two doubly bonded carbons are sp2. but the halogen is being attached to sp3 hybridized carbon, so this belongs to sp3 hybridized carbon of hybridization. Then alkyl, I have RCH2, where if the halogen is present, that goes sp3, and here also halogen is present at sp3 carbon, and one more is benzyl. Benzyl is the derivative, we can say the toluene. Toluene is methyl benzene, in which one of the hydrogen is replaced by halogen. Those are comes under benzylic halide. So depends on the hybridization of carbon, we can classify these halo compounds into sp3 hybridized halo compounds and sp2 hybridized carbon of halo compounds. Further to classification, we may take allyl halides, alkyl halides and benzyl halides, from which we can get the primary, secondary and tertiary derivative of these respective halides. What are primary, secondary and tertiary? See, this is alkyl group representation, this is allyl group and this is benzyl group. In all this, suppose if I have one halogen to it RCH2X, and in which I am going to write CH2 double bond CH2X, and here this benzyl into benzyl halide CH2X. So this is the functional carbon to which the functional group is attached. Similarly, it has the functional carbon with the functional group, and I have this is the functional carbon with functional group. In all these cases, we may find the CH2, it has one alkyl group, and this CH2, it has one vinyl group, that is the ethenyl group, and here this carbon, it has one phenyl group, phenyl it is C6H5. Now let us replace one of the hydrogen of this one by one more alkyl group. So what I will get, I can have R CH, I am going to add one more alkyl group, let us take this is as R dash, so now I am getting X. Similarly, for this CH2 double bond CH, CH with R X, and here I can write that phenyl group along with CH with one R and X. Now you may find the functional carbon, it has two similar or different alkyl group. Similarly, I have this functional carbon with the one vinylic and alkyl. Similarly, here I have this carbon with one phenyl and alkyl. So when the functional carbon has two similar or different alkyl groups or the respective groups attached, then that is said to be secondary alkyl halide. So these are the class of secondary halides. So these are of primary alkyl halides. So these are a class of primary, and these three are the class of secondary one. Next, I have one more hydrogen in their carbon, the functional carbon. So this hydrogen is also being replaced by one more alkyl group. So what I will get, R, C, R2 dash, here R dash with the X. Similarly, I can have CH2 double bond CH, C, R dash, R with the X. Here I can write C6H5 C R dash R X. So these are the compound. You may find the functional carbon, they have different or similar alkyl group, and here too and that too. So such classes of compounds are said to be tertiary alkyl halides. And in this chapter, we must have the knowledge of primary, secondary, tertiary, because this will play a major role in their substitution and elimination reactions. So we need to clarify what are primary alkyl halide, what are secondary halide, what are tertiary halide. Primary, you should find the functional group of CH2X. secondary CHX and tertiary CX. This is what the functional group with the functional carbon. See, we have replaced the functional carbon that has 2 hydrogen, those are replaced by 2 alkyl group. You can't be able to add furthermore any alkyl group to the functional carbon. Why? That functional carbon has no hydrogen and hence no more alkyl groups or any other groups to be added to the functional. So we can have an alkyl halide or benzyl halide or allyl halide in 2 of 3 classes: primary, secondary and tertiary. The next one, nomenclature. Before we enter to nomenclature of monohalo derivatives, see how the dihalo derivatives are named. See, in this case I have an alkyl group with only one halogen, and in the next case the alkyl group, it has 2 halogen atom to the adjacent carbon atom, and in the third case I may find both the halogen atoms to the same carbon atom. So when halogen to one of the carbon, those are generally called it as alkyl halide, but these two are the derivatives of their alkenes. That's why the common name is said to be alkene dihalides. These are said to be alkene dihalides. So these are as a result of addition of halogen to an unsaturated system in which the halogen is added to the doubly bonded system of adjacent carbon where carbons are adjacent. That's why those are said to be vicinal dihalides. And in the case of geminal dihalides, this is also the derivative of alkynes. These are derivative of alkenes. These are the derivatives of alkynes. Alkynes, C triple bond CH system. So if I have C triple bond CH system to which I should add a hydrogen halide. So the hydrogen halide, halogen goes to the carbon with CH, where both halogen to the same carbon and the alkyl group carrying carbon gets hydrogen. So this follows anti-Markovnikov rule. So following anti-Markovnikov rule in the alkyne, we will get the compound of the one having both the halogen to the same carbon. Such compounds are said to be geminal dihalide, where both halogen to the same carbon atom. So gem means same, vis means adjacent. These compounds are named as alkylidine halides. These are named as alkylidine halides. Here alkene dihalide, we are using the 2, but in this case we have to say alkylidine halides. Let us take a proper example. I have taken propane in which one of the hydrogen is replaced by halo. Name is 1-halopropane as far as considering IUPAC name. And here the same propene I have taken which undergoes addition reaction of halogen that makes the position of halogen at the first carbon and the second carbon. So the name is 1,2 dihalopropane. And the second one, the next one, I may find both the halogens are to the same carbon. So it says 1,1 dihalopropane. What about their common name? Common name as per the alkene and alkylidine. So common name for this propyl halide, because of 3 carbon propyl halide. Here it is from alkene, so the name is propenyl dihalide. Here it is from alkyne, so this is propylidine halide. So this is the way how vicinal dihalide and geminal dihalides are named. Let us start how the IUPAC names are given for haloalkanes and substituted haloarenes. So in nomenclature, common name for the halo compounds are given alkyl halide. So alk plus yl plus halide. So alk is the root word, how many carbon we have found, and yl the suffix of the one. So the common name for halogen derivatives given as alkyl halide, and in the IUPAC name the halide group that becomes the prefix of IUPAC name. So in IUPAC we have to take the suffix of halide from common name as the prefix of IUPAC name. So we have to take it as haloalkane. So let us take some examples. See, the first one, I have taken a compound in which first of all I have to identify the longest chain and the functional group and where the functional group is present. This we have to identify. So let us start the numbering. This is the functional group where the functional group is there that makes the part of the parent chain. So I have to start the numbering of bromine attached carbon 1 and the successive are at as 2 and 3. So this is as 3. So I can write even 1, 2, 3 or even 1, 2, 3. So in any direction if I go, the number it takes 1, 2, 3 only. So how to give? First of all, common name. This structure is neopentyl structure. A tertiary carbon with primary carbon. This is called neo structure and it has totally 5 carbon atom. So the name of the first one is given as neopentyl bromide. So this is common name. If I say the IUPAC name where the first position has bromine and the second position of carbon has 2 methyl group. So the name of the compound it goes first of all, we have to, when we find more than one substituent, we should follow the alphabetic order. So Br comes first followed by methyl. So the name is 1-bromo 2,2 dimethyl and the longest chain it has 3 carbon. So the name is propane. So this is IUPAC name of neopentyl bromide. And the next one, I have only 3 carbon but the bromine that occupies the position of second carbon. So this is 1, this is 2 and this is 3. So here it is isopropyl structure. Isopropyl structure is CH3, CH, CH3. This structure is observed as iso. So here 3 carbon I have. So the name is isopropyl. So the name of the compound is isopropyl bromide which comes under common name. IUPAC name, once again I have to find out the position of halogen, that is second position bromine it has. So the name it goes 2-bromo and the longest chain 3 carbon. So root word is pro and its primary suffix is ane. So the compound is 2-bromo propane. The next one, I have a benzene with disubstituent, that is 2 substituents are there. One is chlorine, the other one is toluene. How to name the one? First of all, we have to identify what is the base of the ring. The base of the ring is actually toluene in which the halogen is present. So I can write it is halogen where it is present at the ortho position. With respect to methyl, it is ortho position. So I can say this is orthochlorotoluene. And in IUPAC name, the ortho position turns into second position. The methyl group is first position and the chloro group is second position. So I will write 2-chlorotoluene or I can say 2-chloro-1-methyl benzene. But toluene itself is taken as IUPAC name, so we can write the name as 2-chlorotoluene. So let us take the second one in which the carbon it has 3 times of chlorine atom with 1 more alkyl. For this, actually it is the form of CHCl3 called chloroform, in which the instead of 1 hydrogen I have methyl group. So the name is given as methyl chloroform as common name. And its IUPAC name, the first carbon it has 3 chlorine atoms. So I should write 1, 1, 1 trichloro and there are 2 carbon atoms present, so that makes ethane. So likewise we have the other compound, it has fluorine as the part of chain and the functional group. So fluorine is at the first position, second and third. It has 3 carbon atom. So the name is propyl fluoride. Prop for 3 carbon, yl for suffix, and the functional group is fluorine. So it is fluoride, or it is 1-fluoro-propane. Suppose if you have the compound in the bond line structure, how to name the compound? Let us take this example. That compound is given in bond line structure. So in the bond line, you should know how many carbon are there as a part of parent chain and what are the substituent it has. I find the substituent as bromine, chlorine and 1 alkyl as well as a double bond. Out of this, we should find the priority of the structure. The priority it goes to doubly bond. So the first and the least number should be given to the doubly bonded carbon. This is 1, this is 2, 3, 4, 5, 6, 7. So there are 7 carbon atoms in its structure. So when we name the compound, we should find the substituent according to their alphabetic order. So 3 bromo, 5 chloro, 6 methyl. It represents a methyl group and the double bond to the first position. So the IUPAC name of the compound is 3 bromo and 5 chloro, then 6 methyl, and its root word 7 carbon are there. So hept, and it has a double bond at the first position. So hept 1. The primary suffix of this is -ine due to the double bond. This is how to name the one. Or else you have to write the proper structure of the compound. How to write? This is the CH3 group and in this I have CH with CH3. This is CHCl and another one I have CH2, then CHBr, then CH double bond CH2. This is the proper structure of the bond line structure. So this is also you can identify the numbering 1, 2, 3, 4, 5, 6, either 7 or this 7, that to make the same name. So if you just confuse with the bond line structure, you can make it as a proper structure of the molecule and you can able to name it. Let us see nature of carbon halogen bond. Carbon is bonded with a halogen atom which is actually more electronegative than carbon. So the halogen that can tend to attract the shared pair of electron towards itself. As a result of this, the halogen that develops a partial negative charge and the carbon that develops a partial positive charge. So such one is said to be a dipole. So the halo compounds, they have dipole-dipole interaction in them, and where the halogen is either chlorine, bromine, iodine or even fluorine. So for the same alkyl group, we can discuss about bond length, bond enthalpy and polarity of these halo compounds based on their size of halogen and electronegativity of halogen. We know in the halogen family, on moving down the group, electronegativity decreases. So fluorine is the most electronegative atom and iodine becomes the least electronegative atom. So the electronegativity of these halogen that influence the polarity of the compound. If the fluorine is more electronegative, it can tend to pull the shared pair of electron more effectively and hence the dipole moment of the compound will be greater. That makes the molecule or the compound becomes more polar. So depends on the electronegativity of the halogen, polarity of the bond is found to be RF greater than RCl greater than RBr, which is greater than Ri. R is the any alkyl group. And the next one, bond enthalpy. and the bond length. These two are related to each other. That depends on the size of the halogen. Going down the group, electronegativity decreases, but the size of halogen increases due to the addition of too many number of shells. So, iodine is found to be the largest group compared to fluorine. So, the iodine that makes a large length because of its large size. So, carbon iodine bond length becomes longer compared to carbon fluorine. So, the size of alkyl halide that decreases from iodide to fluoride, and hence the bond enthalpy. When bond length is greater, bond enthalpy will be smaller. That means if the length of the bond is too longer, it requires very small amount of energy to break it. But if the bond length is smaller, it requires high energy. So, based on that, the fluoro compounds have higher bond enthalpy compared to the iodo compound. So, based on this, we can observe the presence of the halide group in the compound and depends on its electronegativity that can develop the polarity between carbon and halogen bond. Preparation of haloalkanes. In this section, we are going to prepare only haloalkanes. Haloarenes let us find later after the completion of the preparation and the properties of haloalkanes. Haloalkane that can be prepared from alcohol, alkane, alkene and by halogen exchange process. Let us take first of all from alcohol. Alcohol generally represented as ROH. So, first of all, when it is treated with sodium or potassium salt in presence of sulfuric acid, where the OH of alcohol is replaced by Br, that is the halogen. So, the product will be Br plus this sodium with acid that makes sodium hydrogen sulfate, OH with the hydrogen of sulfuric acid that forms water. Suppose instead of sodium bromide, if I have sodium iodide or potassium iodide, I should not take sulfuric acid, instead I have to take phosphoric acid. Let us explain why we do not take sulfuric acid in case of the salt is potassium iodide. See, the proper reaction for this is ROH plus Ki in presence of 95% of H3PO4. This is called orthophosphoric acid. I will get the compound RiKH2PO4 plus H2O. These are the products formed. So, in place of Ki, we should take 95% of orthophosphoric acid. We should not take sulfuric acid because it is the strong oxidizing agent that oxidizes the hydrogen iodide produced during the reaction into iodine. The next one with phosphorus trihalide or phosphorus pentahalide. These trihalide and pentahalides are said to be better halogenating agent. Let us replace X by Br. Suppose alcohol with PBr3 phosphorus tribromide, it gives RBr plus H3PO3 called as phosphorus acid. So, in this case also the halogen is replacing OH group. This OH group is replaced by one of the halogen. So, I have 3 halogen atoms. So, the Br or Br is multiplied by 3 times and hence the alcohol should be taken as 3 times. As it has 3 hydrogen and 3 oxygen, that makes H3PO3. Suppose if the reaction proceeds with phosphorus pentachloride, the products will be RCl plus POCl3 plus HCl. So all the 5 chlorine atom of phosphorus pentachloride, one of the chlorine that replaces the OH, and the rest of the chlorine atom that is removed as phosphorus oxychloride and hydrogen chloride. So the OH group is replaced by the halogen atom. The next method of preparation from alcohol with thionyl chloride. So the next we can take with thionyl chloride. Thionyl chloride is SOCl2. This is a very good chlorinating agent, and in this case the alkyl halide produced will be in a pure form. See, ROH plus SOCl2, that gives RCl plus SO2 plus HCl. So in this case we have the OH group that is replaced by one of the chlorine. So I am getting RCl, and SO with this oxygen that is liberated as sulfur dioxide, and the hydrogen with one more chlorine that is also liberated as hydrogen chloride gas. So this sulfur dioxide and HCl are escapable gases. That's why the alkyl halide that is produced in the pure form. So pure form of alkyl halides can be prepared by using thionyl chloride. The next method of preparation of alkyl halides from alcohol is with Lucas reagent. What is called a Lucas reagent? The mixture of concentrated HCl and anhydrous zinc chloride is known as Lucas reagent. So this reagent, when it is treated with the 3 types of alcohol, say primary alcohol, secondary alcohol, tertiary alcohol. Already we have discussed about primary, secondary, tertiary and all in case of haloalkane. Similarly, we can discuss about the CH2OH. It has only one alkyl group, so it is primary. And this functional carbon, it has 2 alkyl groups, so it is secondary. And this functional carbon, it has 3 alkyl groups, so this is tertiary. So when this alcohol reacts with the Lucas reagent, they used to form turbidity. Turbidity means some materials they are suspended in the solution, that is said to be turbidity. So how the turbidities are formed? The primary alcohol with the Lucas reagent that can form the turbidity only upon heating. So at room temperature the reaction won't take place. That's why the mixture of primary alcohol and Lucas reagent is heated up, so we are getting primary alkyl halide. But in the case of secondary alcohol, it reacts with the HCl at room temperature itself in presence of anhydrous zinc chloride. It forms the secondary alkyl halide. But the formation of turbidity that takes little time. So it may take either 5 to 10 minutes to form the turbidity at room temperature. But in case of tertiary alcohol, by simply shaking with hydrochloric acid, immediately that appears the turbidity. That means the reactivity of alcohols towards Lucas reagent that alters. So when tertiary alcohol reacts with the HCl simply by shaking, that means tertiary alcohols are more reactive. So that order of reactivity towards Lucas reagent, we can write tertiary greater than secondary greater than primary, that is towards the Lucas reagent. So in this case, with the corresponding alcohols are converted into alkyl halide. And moreover, why do we take anhydrous zinc chloride? It absorbs the water produced in the reaction. The last one, we have alcohols with the halogen in presence of red phosphorus. The red phosphorus that converts halogen into their trihalides or pentahalides depends on the reaction condition. The halogen is either chlorine or bromine. We won't take either fluorine or even iodine. So in presence of red phosphorus, the halogen is converted into their trihalides of phosphorus and then they react with alcohol. So we should take plus X2 in presence of red phosphorus, that alcohol is converted into alkyl halide, where X is either chlorine or bromine. So this is by which the halogen and the red phosphorus converts alcohol into alkyl halide. Next method of preparation of alkyl halides from alkanes. Alkanes are the saturated hydrocarbon. So in which the halogen that can be substituted by free radical substitution reaction, and we discussed about this reaction in hydrocarbon chapter itself. Let us take methane. It has 4 hydrogen atom. All the 4 hydrogen atom can be substituted by the halogen. So in the first case, it reacts with the chlorine in presence of sunlight. The sunlight is very important. Then only the hydrogen can be substituted by chlorine through the formation of their free radical. So we will get CH3Cl, one of the hydrogen with the chlorine, that is left as HCl. And I have 3 more hydrogen atom in my methyl chloride that can also be subsequently removed by treating with the chlorine. So 1 more HCl is removed. So the product is CH2Cl2. And furthermore, it has 2 more hydrogen. So 1 more chlorine, that makes minus HCl with CHCl3. Finally, that compound has 1 hydrogen that is treated with another molecule of chlorine, where minus HCl. So we are getting CCl4. So in methane, all the 4 hydrogen atoms are replaced by the halogen atom. So we will get the corresponding compounds of chloromethane, dichloromethane, trichloromethane, or it is chloroform, tetrachloromethane, or it is carbon tetrachloride. So these compounds are said to be polyhalogen compounds. The next method of preparation of haloalkanes from alkenes. Alkenes are a doubly bonded system that may undergo either addition of halogen or addition of hydrogen halide. When you do the addition of halogen, the 2 halogen atoms, they can add to the doubly bonded system. So in which the halogen attached to the adjacent carbon, so it gives rise to vicinal dihalides. But at the same time, when hydrogen halide is taken, it will follow the 2 types of mechanism. One is Markovnikov mechanism and other one is anti-Markovnikov or peroxide or Karash effect. When this will be followed, if the taken alkene is unsymmetrical. See, I have taken propene, both of them are unsymmetrical. If I take symmetric alkene, no need of worrying about Markovnikov or anti-Markovnikov. The hydrogen halide will be added to both of the carbon, double bond carbon. But in case of unsymmetrical alkenes only, we have to consider, depends on the reaction condition, whether it follows Markovnikov rule or anti-Markovnikov rule. Markovnikov rule that takes place through the formation of carbocation, in which the tertiary carbocations are more stable than secondary, which is then primary. But anti-Markovnikov that follows only the reaction that has peroxide. So in this case, the peroxide that generates the free radical, then those free radical undergoes addition reaction between the doubly bonded carbon. In this case also, the tertiary free radicals are more stable than secondary, which is then primary. So anti-Markovnikov product is always primary product and Markovnikov product is always secondary or tertiary product. So the mechanism of these reactions also discussed in hydrocarbon under alkane part. So let us see the halogen atom of that hydrogen halide. According to Markovnikov rule, the halogen goes to the carbon with more alkyl substituent and the hydrogen is by the carbon with less number of alkyl or no alkyl group. So halogen to the secondary carbon, it forms a secondary product. But in presence of peroxide, the halogen should go to the carbon with no alkyl or less alkyl group, and the hydrogen goes to the carbon with more alkyl. So I am getting CH3, CH2, CH2X. So the primary product will be the product. Halogen exchange reactions, in which one of the halo compound is converted into other halo compound, in which we can have the two different reaction. One is Finkelstein reaction, the other one is Schwarz reaction. Finkelstein reaction that converts chloro or bromo compound into iodo compound. So to convert chloro or bromo into iodo, it requires the reagent. So the Finkelstein reagent is sodium iodide in acetone. So when you take sodium iodide in acetone, where the iodide replaces the bromide group, so we are getting alkyl iodide, in which the salt formed sodium bromide becomes insoluble in acetone, because acetone is a nonpolar solvent in which the ionic compound becomes insoluble. So the presence of sodium iodide in acetone, that indicates the reaction is Finkelstein reaction. Similarly, let's go with Schwarz reaction. In this, I am going to convert chloro-bromo compound into fluoro compound. That can be done by taking the metallic fluorides like silver fluoride, mercurous fluoride or mercury 1 fluoride, antimony trifluoride or cobaltous fluoride, or it can be cobalt 2 fluoride. So by taking either of the metallic fluorides, the bromo or chloro group can be replaced by the respective fluorine atom. So we will get fluoro compound with silver halide. So such name reactions can be understood only from their reagents, because for name reactions the reagents are highly specific. One of the sodium iodide in acetone you can't able to find out in any other reaction. So name reactions can be viewed only by knowing their reagent and what kind of compound is getting converted into what kind of product. So these two information we should know as far as considering the name reactions. Okay students, we have completed our today's session. In this session, we have seen about classification of halo compounds, their nomenclature and the structure of carbon halogen bond, and also we studied about the preparation of haloalkanes. So let us see in our next class with the properties of haloalkanes. Until then, bye bye.